Welcome to Brain Vision.
Our question is: consider an ideal gas turbine cycle with one stage of compression and two stages of expansion and regeneration. The pressure ratio across each turbine stage is the same. The high pressure turbine exhaust gas enters the regenerator and then enters the low pressure turbine for expansion. To the compressor inlet pressure, determine the thermal efficiency of the cycle as a function of the compressor pressure ratio and the high pressure turbine to compressor inlet temperature ratio. Compare your result with the efficiency of the standard regenerative cycle. So first we will draw the TNS diagram. TS diagram like this. This is one, two, this is the fifth point, six. This is the heat output. This is point three, four, and seven. This is heat input. Q in. This is the fourth point. This is the diagram for this question. We will write the overall pressure ratio of the cycle is Rp, which is the pressure ratio across the compressor. So the pressure ratio for a compressor. Now the turbine's pressure ratio in the ideal case will become equal to Rp under root. That is for turbine. Now using the isentropic relations, now using isentropic relations, temperatures at the compressor and the turbine exist. Temperature at the compressor and turbine exit can be expressed as T5 is equals to T2, that is equal to T1 into P2 divided by P1 power K minus 1 divided by K, which is equals to T1 into Rp K minus 1 divided by K. So temperature T7 is equals to T4, which is equals to T3 into P4 divided by P3 power K minus 1 divided by K, which is equals to T3 into 1 over under root Rp. This is the compression ratio for a turbine, pressure ratio of a turbine. K minus 1 divided by K, this will equals to T3 Rp power 1 minus K divided by 2K. Now T6 is equals to T5 into P6 divided by P5 power K minus 1 divided by K, which is equals to T5 into 1 divided by under root Rp power K minus 1 divided by K, which is equals to T2 Rp 1 minus K divided by 2K equals T1 Rp K minus 1 divided by K Rp power 1 minus K divided by 2K. It will become T1 Rp into power K minus 1 divided by 2K. Then our heat input Q in will become equals to H3 minus H7 is equals to Cp into T3 minus T7, that is Cp T3 into 1 minus Rp power 1 minus K divided by 2K. So our heat out, that is Q out, is equals to H6 minus H1 is equals to Cp into T6 minus T1 equals to Cp T1 into Rp K minus 1 divided by 2K minus 1, and thus thermal efficiency is equals to 1 minus Q out divided by Q in, 1 minus Cp T1 Rp K minus 1 by 2K minus 1 over Cp T3 1 minus Rp 1 minus K divided by 2K. Now we will simplify this equation, and after simplification we will get the relation for thermal efficiency as 1 minus 1 over T1 divided by T3 into Rp K minus 1 by 2K. The thermal efficiency of the single stage ideal regenerator cycle is given by 1 minus T1 over T3 Rp power K minus 1 divided by K. For an ideal regenerative cycle. Therefore, it is concluded that the regenerative cycle with two stages has higher thermal efficiency, has higher thermal efficiency than the standard regenerative cycle. Than the standard regenerative cycle with a single stage of expansion, with a single stage of expansion, with a single stage of expansion for any given value of pressure ratio, for any given value of pressure ratio Rp, of pressure ratio Rp. This is our answer. Thank you.